And we're back for yet another example of how to do utility maximization, calculate income and substitution effects using the Hicks-Kaldor method. Just throwing that out there because there's two different ways you can do it. One way is the Slutsky preferred method of illustrating the Slutsky equation. We're going to use the Hicks-Kaldor method of illustrating the Slutsky equation and breaking into the total change into two parts, income and substitution effect. So this is just yet another example. We'll also talk about the compensating variation, and we're going to graph our results down here on this page. So I have two different copies of the graph. And please, I encourage you, go download this handout. It's a PDF. It's on my website, www.berkeyacademy.com. And I'm going to call this file this long, annoying name. Just go to my website and click on Files. On the left side, you'll see Files, and then I'll call this income.subs.another.example.pdf. And you can download it, and you can work it along with me at home, and you can do the graphing part and interpretation part. So let's get going. I'm going to make this a quick example. I'm going to assume you know how to do this. This is just another example for practice for you to do. So let's suppose the utility from gasoline and all other goods. So we're thinking about gasoline as being the X variable here on the X-axis, and we're thinking about all other goods being the Y good on the Y-axis. And this is a typical example where you don't want to look at two goods. You want to analyze and focus on one good, and then all other goods you're going to call, sometimes we call this a numeraire good. It's just, let's assume that everything else costs $1 a piece, and that represents all your other opportunities. Now I'm going to stick with this Cobb-Douglas Utility Function for this example, because it's simple to work with and simple to do the marginal rate of substitution. So if this is this person's utility function, the amount of gasoline to the 0.2 times y to the 0.6, let's assume initially this person has a budget of $100, price of gas is 60 cents a gallon, and the price of all other goods is $1. Now 60 cents a gallon is low because what I'm trying to think of here is modeling the low prices of gas in some of the Middle Eastern countries that subsidize gasoline. And what we're going to be doing here is analyzing the impact on a typical consumer, modeling the impact on a typical consumer, if they were to remove the subsidy and raise the price from 60 cents a gallon to $1 a gallon for the price of gas. So let's get to work and start solving this. So I'm going to use the marginal rate of substitution equals the ratio of the prices method of solving this. So the price of X, which is gasoline in this case, and the price of the Y good. So when we fill in using our shortcut method for Cobb-Douglas utility functions, we're going to get that the marginal rate of substitution is 0.2y divided by 0.6g, or x. I'm just going to leave it as x, just to try to make it a slightly less confusing here. I like to do that because then we know which variable is going to be graphed on the x-axis is going to be the x variable. So x is going to stand for our gasoline. The price of gasoline, we're assuming, is 0.6, and the price of all other goods are $1 a piece. So this is our first equation. Our second equation is going to be simply the budget line equation. The budget line equation here is going to be 0.6 times how many x's we buy plus 1 times how many y's we buy equals $100 the budget. And we just want to solve these two equations into unknowns. So we're going to solve this equation on the left for either x or y, plug it in to the budget line. Now if we solve this for y, we'll get y equals 1.8 x's. And then if we take that and we plug it in for y into the budget equation over here, we'll get 0.6x plus 1 times 1.8x equals 100. And we're going to collect those two x's. We'll get 2.4 x equals 100. And the amount of x is going to be 41.6 repeating. So our x star, our optimal amount of x that we should buy in this case, 41.66666. I'll just round that off to 41.67. Then we can plug that number back into any of the equations we have to figure out the optimal amount of y. Now, the easiest thing is to just use this equation right here. Y equals 1.8x. Multiply this x by 1.8. And what you'll get is a number very, very, very close to 75. In fact, you'll get something slightly different if you round this off like I did to 41.67, but the answer without rounding would be 75. And then we want to know how much utility does this person get in this situation. So we plug this x and this y back into our utility function up here and see how much utility that's going to give this person. And when you plug that in, you're going to get that the utility level will be 28.12. We're very, very close to that. Now what we want to do is see what's going to change. So again, in this little example, what we're thinking about is a government is subsidizing the price of gasoline. And they're keeping the price artificially low, and they're subsidizing each gallon by 40 cents, just to keep this simple. So, after they remove the subsidy, the price of gasoline will go up to $1. How is that going to change the optimal consumption pattern and change the utility of our consumer? Okay, well, we're going to have two equations and two unknowns. So, equation number 1 is going to be marginal rate of substitution function 0.2y over 0.6x equals, and now it's the price of gas divided by the price of all other goods, which is 1 over 1, which is just simply 1. Our second equation, the budget equation, is going to be the price of gas times x. So again, we're going to call the gas x. So it would be 1x plus 1y equals 100. Alright, so if we take this first equation and we solve it for either y or x, let's solve it for y again. Doesn't matter. You get y equals 3x. And we'll plug that in for y over here. And we're going to get x plus 3x equals 100. So that's going to give us 4x's equals 100. X, therefore, will be equal to 25. Y is equal to 3x. So, y is 3 times that. Y equals 75. And how much utility is this person going to get now? Plug the 25 and the 75 back into that utility function, and that'll tell us how much happiness this person is going to get. And we're going to see when we plug that in, you should get a utility figure of around 25.4 or so. 25.39. So, let's graph these two solutions to see what's happening. Let's go down to the second page of the handout here and let's graph these two solutions to make sure that they're right and to get some little intuition about what's happening here, to make sure our intuition's right. But basically the idea is that when the price of the X variable, the gasoline, goes up, we should see the person buying less gas, and we do. They go from purchasing 41.67 gallons of gas to 25 gallons of gas. But let's look at these solutions on the graph, graphing the budget lines, and see if these make sense. Okay, so let's go to our graph with our indifference curve map here, our utility map. And I've graphed 5 indifference curves here. So I've got a little legend over here on the right hand side. So I've graphed the indifference curves for 20 utils, 25, 28, 30, and 35. And our two solutions so far should be pretty close to the 28, which is the one in the middle. Kind of a dark blue, I guess, there. And the brown one, the 25, since our second amount of utility is a little bit higher than 25 utils. So let's graph these two budget lines. So the first budget line, we have $100, and the price of our Y good is $1 each. So that means that we're going to be able to afford 100 units of all other goods, priced at $1 a piece. With gasoline priced at 60 cents each, 100 divided by 0.6 says that if we spent all of our money on X, which is the gasoline, or petrol, we could afford 166.6666 gallons. So that's going to put us over here just a little bit higher than 165. And we want to graph a straight line between those 2 points. Okay. So I drew the line, it looks like a little bit too low. My ruler slipped a little bit, but nevertheless, we can see that this line is going to be tangent to an indifference curve right around in here. Now it should actually touch and even cross that indifference curve for 28 utils just a little bit. But again, my ruler slipped. But let's look at our solution. Our solution was 75 Ys and 41.67 X's. So let's graph that point. So a little bit more than 40 on the X, and we should be looking at about 75 on the Y. And so that looks like it checks out. And it looks like the slope of the budget line is equal to the slope of the indifference curve at that point. Okay, so this is our solution number 1. Let's graph the second budget line after the price of gasoline increases to $1. After a subsidy is removed, at that point, these people would be able to afford only 100 gallons of gas, but still 100 units of all other goods. And so the budget line is going to get a little steeper. So, let me see if I can draw a straight line there. Alright. And so this is the budget line, a little steeper, with a slope of 1 instead of a slope of 0.6, like this original budget line has. And the solution that we got was X should be equal to 25, and Y should be equal to about 75. Okay, so that looks pretty good, like that's where those two are going to be tangent. So that's solution number 2. So we're seeing here that when the price goes up, of course, you're going to buy less. Now, part of this exercise is before the price increase, people are buying 41.67. So let's write that down here, 41.67. After the price increase, people will be buying, or this example person will be buying 25 gallons of gasoline. The Slutsky equation says that we can split those two, split this total effect into two. We can split the total decrease from 41.67 to 25 into two separate parts. Part of it will be an income effect, because this person feels poorer, because this person's buying power is lower. And the other effect is the substitution effect, which is because the opportunity cost of y relative to x has changed. And that opportunity cost is reflected by the slope of the budget line. So you can think about the substitution effect as being solely that effect because the slope of the budget line is changing. So what we do is we go back and we do a third problem, and this is a hypothetical solution. Sometimes we call this the decomposition basket. So now determine the hypothetical decomposition basket, where people would get the same utility as before. So we're thinking about the old utility level, but at the new prices. Old utility, new prices. So we need to set up two equations that we can solve to get our two unknowns. And these two equations are going to be, the first equation will be exactly the same as this equation from the second problem. And what this guarantees is that the marginal rate of substitution, 0.2y over 6x, so 0.2y over 0.6x, is equal to the ratio of the prices, the ratio of the new prices after the price change, which is 1 over 1. So that's the same equation that we used in number 2. Now the second equation is going to be the fact that we want our utility to be the same as it was before. And our utility in the first problem was 28.12. So our second equation is 28.12. That's what we want our utility to be. Set that equal to the utility function. X to the 0.6, x to the 0.2 times y to the 0.6. So x to the 0.2, where this is the gasoline, times y to the 0.6. And what this does is guarantee that whatever values for x and y we solve for here, that it's going to give this person the same utility as they had before the prices went up. So it's going to get them back to that old utility level. Alright, so let's solve these two equations here. Now since this equation is the same as in problem number 2, then this simplification, y equals 3x, is also going to be the same. So y equals 3x. Now what we want to do is take this y equals 3x, substitute it in this second equation for y. So we have 28.12 equals x to the 0.2 times 3x to the 0.6. And you want to make sure that you raise both the 3 and the x to the 0.6, because if y is 3x, we want to raise everything that is part of y up to that exponent, the 0.6. Now what you want to do is distribute that exponent, the 0.6, to both the 3 and the x, so we can rewrite this way. So x to the 0.2 times 3 to the 0.6 times x to the 0.6. And then we want to collect those two x terms by adding the exponents. Alright, so that's going to give us x to the 0.8. Let's go ahead and figure out what 3 to the 0.6 power is. And 3 to the 0.6 is about 1.933. So times 1.933. That's equal to 28.12. Make myself a little bit more space here. Okay. Now divide both sides by the 1.933. So 28.12 divided by 1.933 gives us 14.55 roughly, equals x to the 0.8 power. And then what we want to do is raise both sides of this equation to the 1 over 0.8 power. So that leaves us with x on one side equals, raise it to the 1 divided by 0.8 power. And we get that x is going to be about 28.41. Okay. Now, what's y going to be? Well, to get y, we use this little trick, this little equation over here, that y is 3 times x. So 28.41 times 3 gives us 85.23. And if we plug those two values back into the utility function, they have to give us 28.12 as the utility you're going to get for consuming this amount of x and this amount of y. Now, something we want to know at this point, though, is how much. We know the utility, but how much would this cost? What we're really looking for in this hypothetical basket is we're asking the question, if we want to get this hypothetical consumer back to their old utility level, what's the cheapest way to do it? What combinations of x and y would be the cheapest way at these new prices to get this person back to their original level of happiness? So, if we want to know what the cheapest way is, it makes sense that you want to calculate how much that's going to cost. And this is really easy in this problem because we're talking about the new prices are $1 for the price of gas and $1 for the price of all other goods. Well, the budget equation is just $1 times x plus $1 times y. How much is that going to be? So we take 85.23 plus 28.41. And we find out that this would cost us about $113.64. So the budget would be approximately, because we're doing some rounding here, so if you get a slightly different answer, then that's okay, but $113.64. Okay. Which is more than our original budget, which makes sense, because when the price goes up, we're not going to be able to get this original utility level with only $100. It's going to take a little bit more money in order to do that, $113.64 in this case. All right, let's graph this hypothetical or decomposition basket solution on our graph. Why? Well, because it does two things. It helps us make sure that our answer is correct, make sure we didn't make any kind of mathematical mistakes, and second, it helps us visualize the income and the substitution effect. So let's go down to our graph and graph this. $113.64 is our budget. So when we go down here to our indifference curve map, and we want to draw our budget line, then, here, let me draw this budget line in red. With $113.64, we could afford 113.64 units of all other goods, and we could afford 113.64 units of gasoline, since the price of gas is $1. And so our new budget line for this hypothetical solution should be parallel to our solution that we did in problem number 2. but the answer is going to be different. And what we're doing here with this hypothetical solution is we're rotating this blue budget line around, kind of wrapping around this indifference curve right here, right? So this indifference curve that tells us all the different ways we can get about 28 utils. We're wrapping around saying, well, when the slope of that budget line changes, if we wanted to get the same utility level, how much X and Y could we buy to get that same utility level, but for the cheapest price? So our solution was 28.41 X's and 85.23 Y's. So going to be a point here close to, but not quite at 30. So here is solution number 3, that hypothetical basket. So when we break apart the total change here in the amount of gas bought, the amount of X, that's a difference here of about 16.67, right, between 25 and 41.67. What this hypothetical decomposition basket does is it allows us a way to break that total change into 2 parts. And so here's the total change in yellow. That point allows us to split it. And part of this is going to be the income effect, part's the substitution effect. Which is which? Well, easy way to tell is what's happening here when we go between the red budget line and the green budget line. It's a parallel shift downward. Parallel shift downward. Now, a parallel shift of a budget line means that we're giving you either more income or less income. And so the movement between the solution on the red budget line and the green budget line, that's the income effect, right? So when we split this total impact into 2 pieces, again, that number, that X number is 28.41 units. Let me write that down. 28.41. So we see the total decrease there is about 16.67 units. This smaller part right here between 25 and 28.41, or 3.41 units, that is the income effect. Very small in this case. The remainder is the substitution effect. The reaction that consumers have because of the relative price change. Now gas is relatively more expensive compared to all other goods than it was. It used to be cheaper. Now it's the same price as all other goods. It's $1. So this larger section here between 28.41 and 41.67 is the substitution effect. So 41.67 minus 28.41 is 13.26. So the 3.41 is the income effect. The remainder of that 16.67 change, 13.26, is the substitution effect. And when you add those two together, you need to get the entire change, 16.67. So to summarize, when you raise the price of gasoline, or you take away the subsidy, which causes the price to rise, this analysis will predict that the typical consumer might decrease their purchases of gasoline by 16.67 gallons per week or per month, total. And most of that in this case is due to the substitution effect, due to the relative price change, and only a small part of it is due to the fact that the consumer feels poorer, or their consumption possibilities have been decreased due to this price change. Now, this also kind of makes sense. When you do a lot of these problems and you think about the results, the income effect here is fairly small. Again, that means that this is the portion of the decrease that's due to them feeling poorer. What we saw is, well, how much money would this consumer need to make them just as happy as they were? It's a relatively small increase, $13.64. So we did this fourth part here where we analyzed how much of the change was due to the income and the substitution effect. So the next part, kind of the final part of this problem, is let's calculate what we call the compensating variation. So the compensating variation is asking the question, how much money would it take to get this person back to their old utility level at the new prices? Okay, so that's compensating variation. How much change in budget, to be very precise here, change in budget. How much more money or less money would it take to get this person back to the old utility level at the new prices? To get to old utility level before the price change at the new set of prices. And the budget that you need to get the old utility level at the new prices, we calculated right here. The budget would be $113.64. But the compensating variation is the change in the budget that you need to get back to the old utility level at the new prices. So the change in the budget, our original budget was $100 before the price change, is all we needed to get to that level of utility. Now we'd need $13.64 more. So the compensating variation is going to be this $13.64 difference in our original budget of $100 compared to our budget required after the prices to get us back to that old level of utility. There's also another measure called the equivalent variation. And I have a video where I go through how to calculate the equivalent variation and what that is. I'll just repeat quickly the difference between equivalent and compensating variation here. The compensating variation, think about that word compensate. Compensating variation, just think about variation as change in budget. Compensating variation is asking how much money would it take to compensate someone for the price change. Now, if it's a price increase, you're going to have to give them more money, so that compensating variation will be a positive number. However, if it was a price decrease, the compensating variation would be a negative number. Why? Well, because when you lower a price, that makes somebody better off. It makes them happier. And so, what's the change in budget to get people back to that old, lower utility? Well, we're going to have to take money away from them at these new lower prices. So you can have a negative compensating variation. Equivalent variation, on the other hand, so equivalent is another way of answering the question, well, how much money is this price change affecting us by? If we wanted to equate it in terms of a change in income or a change in budget. So compensating variation, instead of asking how much money would it take to compensate us to get us back to the old utility level, equivalent variation asks, in this case, this price went up. Our utility is going down. How, instead of changing the prices, instead of raising the price of gasoline, I could lower your utility another way. instead of raising the price of gasoline. I could lower your utility just by taking money from your budget. The equivalent variation answers the question, how much money would I have to take from you, from your budget, at the old prices to get you to this new lower utility? Right? So it's a similar kind of calculation, a similar kind of idea, but instead of being the change in budget to get you to the old utility at the new prices, it's the change in the budget that it would take to get you to the new utility at the old prices. A different way of looking at how much money change is this change in prices worth? How much does it hurt you when this price goes up? One way is to ask how much money would it take to compensate you to get you to the old utility level. One way is to ask how much money we could take from you, in this case, to get you to this new lower utility level if we were to keep you at the old prices. Alright, this has been fun. If you have any questions, please post a question in the comment or question section below, and I'll be happy to try to help you by answering any questions you might have. Otherwise, this is Berkey Academy signing out. Good luck with your microeconomics.